So this is actually the first problem that we're going to go through. Sample problem 20.3 basically is just asking us to calculate what delta S of the universe is, and again, state whether the reaction occurs spontaneously at this temperature. So this, again, we haven't really done too much with this, so I'm going to move on to the solution here to sort of just walk through how to think about this problem. Okay, so they tell us that at 298 K, the formation of ammonia has a negative delta S of the system. So again, they tell us what the delta S of the system is. So this is the entropy of that system, and it's negative. So that means it's unfavorable. Okay, so again, they want us to calculate delta S of the universe. So I'm going to flip through and just kind of walk through this because it is something new. So remember, delta S of the universe, we said, is always going to be positive for a spontaneous process. And we know that delta S of the universe is contributions from delta S of the system, which they tell us, and delta S of the surroundings. And we know we can calculate delta S of the surroundings using this equation. Delta S of the surroundings equals negative delta H of the system divided by T. Okay, so one of the things that kind of brings this problem together is, maybe you remember from chapter 6, if not, we're going to review it in a little bit. We can use Appendix B to calculate delta H of the system. Do you remember that Appendix B where we would look up delta HF values and you'd have to put what the values were for each of these specific components in your chemical reaction? And then it was products minus reactants, all of that. We'll review that in a little bit here and practice it again if you don't remember it fully. But that's how we're going to get this piece of information, since it wasn't what was given. They give us the temperature of the system, okay? And so delta S of the surroundings being delta H of the system divided by the temperature is going to end up being 308 joules per Kelvin. Okay, so that's how we're going to get this piece. They give us the delta S of the system. We're going to need to do a little bit of work to calculate delta S of the surroundings, but adding these two together is going to be what gives us delta S of the universe. So wrapping this problem up, adding in the delta H of the system, which was provided at negative 197 joules per Kelvin, adding that to the delta S of the surroundings, which is positive 308 joules per Kelvin. Adding those two together gives us the delta S of the universe as positive 111 joules per Kelvin. So that's our final answer here. So if we want to answer the question, state whether or not it occurs spontaneously. Remember, for a spontaneous process, we want to have positive delta S values. So yes, this is a spontaneous process. Okay, so again, two parts to this problem. Recognizing that delta S of the universe is a combination of both of these pieces, one which is given directly to us, the other one we needed to calculate. Now this problem would have been easier if they just told us what delta H of the reaction was, but we had to rely on a skill we learned in Gen Chem 1 and Appendix B in order to calculate that value. If that's still a little bit fuzzy for you, we're going to do some more problems in just a minute that allow us to think about Appendix B again. And so we're going to have an equation or an equation here, a chemical reaction that we'll look at it for. But I'm going to flip here. I've got Appendix B for you. So hopefully you'll see it here and you're like, oh yeah, I remember Appendix B. When we did stuff last year, all we did was look at this column. Remember, you had to find the right sort of phase that you maybe had for something, and then you literally just grabbed the number off the table. So all we're doing is that same kind of a problem, but we're just using a different column of data. We're going to use the entropy data now. Okay, so I've actually provided it here for you. We've got the 3 pages that we have for Appendix B. So I want you guys to try doing that for this problem. Hopefully you remember how to do it. Again, just a little heads up, how I liked to solve these problems when we did them in Gen Chem 1 is write the value from Appendix B for each of these species underneath its corresponding species on our chemical equation. Make sure to multiply ones that have coefficients, and then take products, sum up all of these values, and subtract the sum of all your reactants. So go ahead and try that right now. Again, see if you're able to get to the correct answer. Let me tell you what the correct answer is here so you can check your work. The correct answer should be minus 374 joules per Kelvin. So pause the video, go ahead and try that, and then when you're ready, press play to see the worked through solution. All right, moving on to the worked out solution here. This also asks us to predict the sign of delta S of reaction if possible. So let's kind of go through that piece first. So if we want to just sort of predict what we think, here's how you might predict what's going on with the reaction. The first thing you want to do, remember, we always talk about more molecules moving more. And this is really only relevant for gases. So the first thing you want to do if you want to predict entropy, count the number of gas molecules on each side. If we are making more molecules, we would predict that entropy is favorable. It's going to be positive. It will be increasing. In this case, we actually make fewer molecules. So entropy should be decreasing, and that's unfavorable. Okay? So again, here's what we need to have here. You write down your balanced chemical equation. Go ahead and look up those values that we have for these species on Appendix B. So if you need to, go ahead and pause and make sure you can find each one of these species on Appendix B. You have to make sure you grab, this was a common mistake for students in Gen Chem 1, make sure you're looking at the phases of the substances so you grab the right value here. Okay, then we need to take products minus reactants. So notice what I did here. I've got 3 moles of CO2, so it's 3 times 213. I'm adding that to 4 times 69.9. Okay, so these essentially are my gains. So I'm going to have these guys here. And then I have to subtract off my losses. So it's 269.9 times 1, and then 205 times 5. So that's where I get that piece. Again, probably it's worth kind of summing all of that up together, summing all of this up together, and then taking the difference, which again is going to be minus 374 joules per Kelvin.